Welcome back. So entropy, depending on the situation, entropy can be expressed in two ways. Entropy can either be a function of temperature and volume, or there's an option that entropy can be a function of pressure and temperature and pressure, whichever order you like. And whichever form of this, whichever one you use, depends on the situation and circumstances in the problem given. Now, in order to determine ultimately which one of these functions to use, we're going to have to know, is it isobaric, is it isochoric, or isothermal? Now, one thing to remember with each of these, remember for isothermal, delta T is 0, okay? For an isochoric process, delta V is 0, and for an isobaric process, delta P is 0. So keep those in mind. Now, recall that we're talking about heat here. For an isothermal process, the heat is given by plus or minus, and I have this plus or minus here because it's going to depend on the situation as heat flowing in or out of the system. But the heat magnitude, at least, is given by nRT over V dV for an isothermal process. For an isochoric process, the heat's magnitude is given by nCV dt. And for an isobaric process, the magnitude is given by nCp dt. Okay? We're going to use these definitions right here for reversible processes or for the system calculation for an irreversible process. So it's very important to be able to do that because in every case, we're going to have to do that for the system. Okay? Now, one thing I'm going to do first is I'm going to show you how to calculate delta S, assuming it's a function of temperature and volume. And then we'll go into which one of these do we want to use, temperature and volume or temperature and pressure, okay? So I'm going to start out with the total derivative or total differential of entropy with the assumption that we're doing temperature and volume first. Now, if you go back and watch the total differential video, it'll explain the mechanics behind it exactly, but here I'm just going to assume that you're familiar with it, okay? So here's what we do. We say integral of ds is delta S, but ds is equal to the integral from t1 to t2 of the partial of S with respect to t at constant v dt plus the integral from v1 to v2 of the partial of S with respect to v at constant t dv. Now, obviously, if we didn't know anything else, these partial derivatives right here, they could probably be pretty difficult to work with if we didn't know what they were. Fortunately, we have what are known as Maxwell relations, and we do know what they are if you've watched the Maxwell relationship video, and they are things you should memorize. When we're looking at the partial of S with respect to t at constant v, that is equal to the heat capacity at constant volume over temperature times dt, okay? If you had a function for CV, you would plug the function in here. If your CV was a constant over the range of temperatures, you just plug in the constant, okay? Partial of S with respect to V at constant T, that's shown right here. This partial derivative is actually equal to the partial of P with respect to T at constant V. So if I'm dealing with an ideal gas, I need to get it in terms of P. So for an ideal gas, P is equal to nRT over V. And then if I take the partial of that with respect to T, then it's nR over V. So then I just plug in nR over V right there. And then that is times dV integrated from V1 to V2. All right. So ultimately, this is the integral that you'll use. Okay. Now, this CV, I don't want to go ahead and integrate that because it could be a function or it could be a constant. I don't know. However, if I did want to go ahead and integrate this part right there, then that would simply be nR times, if I integrate 1 over V dV, that's the natural log of V2 over V1, okay? And that's when I evaluate it from V1 to V2. So this is equivalent to this integral right there, all right? If I had another kind of gas, like a van der Waals gas, I would use the van der Waals equation of state right here to get an expression for the partial of P with respect to T, and I would plug that in and integrate it with respect to V. All right, but in any case, this right here, I'm just going to actually do the pen to do this. I won't box it. This is the expression right here that you'll want to use or at least if I want to use this part. This is the expression when you're dealing with entropy if you want to do it as a function of temperature and volume. Okay? Now what I want to do instead is I want to do the same thing, but now let's assume entropy is going to be a function of temperature and pressure. Okay? Well, I'm going to do the same thing. I'm going to use this total differential method. Integral of ds is delta s, and that's equal to the integral from t1 to t2 with the partial of s with respect to t at constant p dt plus the integral from p1 to p2 of the partial of s with respect to p at constant t dp. All right, so how do I deal with this? Well, one of the Maxwell relationships that's very useful is that the partial of s with respect to t at constant p, this is actually just cp over t. All right. And then you would just multiply that times dt and integrate it. Cp could be a constant over the range of temperatures, or a function would have to be given. The partial of s with respect to p at constant t, okay, partial of s, okay, that is actually, I think I have it over here, the partial of s with respect to p at constant t. This is actually another Maxwell relation, and it turns out this is actually equal to negative partial of v with respect to t at constant p. Okay, now again, I'm going to use the ideal gas because it's the easiest and just it illustrates the point. The variable I want to be explicitly expressed as is v, so I'm going to say v is equal to nRT over p. Then I'm going to take that derivative, the negative of it that is, and the derivative is going to be negative nr over p. Okay, and that's exactly what you see plugged in right here. nr over p, and since it was negative, I pulled the negative out here. I multiply by dp and integrate from p1 to p2. Now, obviously, if this part right here, that integral, the second term was, if I wanted to evaluate that, it would be minus, well, if I integrate 1 over p dp, I'll keep the nr, and then I'll just have natural log of p2 over p1. Okay, and that would be if it was an ideal gas. All right, and so I have these two terms right here. Okay, the temperature dependent term and the pressure dependent, and when I add those two together, or in other words, take the difference, that's going to be the entropy change. Okay, now the question is, why would I ever? When would I ever want to use? How do I know which one to use? That's the important question. Well, let's think about this from the ideal gas perspective, the equation of state. I have a system, and I have a system where the equation is PV is equal to nRT. All right? Now, by specifying any two of these variables, and I'm going to assume that we know the number of moles, by specifying either P or V, I know T. If I specify T or V, I know P, and so on and so forth. So that ultimately means that this is a function of pressure, volume, and temperature. So if I'm already specifying two variables, the other one is automatically specified, okay? Which means that that's why I can sort of put temperature right here, pressure right here, and I don't even have to worry about the volume in that equation. And here, I can specify the temperature and volume, and I don't have to worry about the pressure. So so either one of these equations, whatever you use, it's going to give you the exact same answer. You can use both of them. The thing we want to do, though, is simplify. Let's consider an isobaric system. So if delta P is 0, then in this second entropy calculation, then this term right here would go to 0 if delta P was 0, right? And then all you have to worry about is this simple integral right here, just one of them versus two. Now, if I had an isobaric system and I chose to use the one on the top, there's no place for delta P to cancel because this is dt and dv, right? So that means I would have to evaluate both of those integrals, and it becomes a lot more complicated. So if I have an isobaric system, I'm going to choose the equation that makes it simpler. In this case, it's the second one because dp is 0, so I only have one integral. What about a case where we have, let's say, an isochoric system, all right? If I have an isochoric system, that means what? There's no change in volume, meaning delta V, and therefore dV are 0. So if dV is 0, which one of these equations am I going to use to simplify it? Well, I'd use the top one, right? Because if I use the bottom one, there's no place for dv to go to 0, which means then I have to evaluate both of these integrals. Okay. However, if I know that dv is 0 because it's isochoric, then this integral cancels when delta v is 0. And so then I only have to evaluate one integral, this heat capacity integral right here. All right. And that greatly simplifies it versus having to do 2 here. Now, for an isothermal system, I can actually use both of them, okay, for an isothermal system. If it's isothermal, then delta t is 0, right? So if it's isothermal, then this one goes to 0 when delta t is 0. This integral goes to 0 when delta t is 0, right? And so then that leaves one integral for both of them. And the one that you would probably want to use is whichever one you have the information to do, right? If you don't have the information, if you don't have any volume information, and all you have is pressure information, then you want to use the second one. If you don't have pressure information, all you have is volume information, then you use the first one. Now, you could go ahead and calculate the volume if you knew the pressures. You could calculate the volumes using the temperature, using the ideal gas equation. That's just way too much work. Use whatever is simpler. If you have pressure information and it's isothermal, just use the second one. Okay. Likewise, if you have volume information and no change in temperature, use the first one. All right.